Einstein, as you know, in 1905, put forth this theory that he called Photon Theory. The idea that light, or EMR of any type, exists as a particle, not just a wave. That particle has an energy that's equal to h times f. In other words, the energy of light, according to Einstein, is not related to the intensity of the light. Rather, it's related to the frequency of the light. Ultraviolet light is therefore more energetic than visible light, and visible light is therefore more energetic than, say, microwaves or infrared. That's a big deal, because that explained for us a concept, an observation that had been made as early as 1887 that we call the photoelectric effect. The photoelectric effect says when light strikes a piece of metal, sometimes an electron is ejected. Sometimes it is, sometimes it isn't. From 1887 through 1905, nobody could explain using the wave theory of light why certain observations of the photoelectric effect were made. In other words, why, when we increased the intensity of the light, electrons still weren't ejected. Or why, when we changed the type of light from visible light to ultraviolet, electrons were ejected. This photon theory explained that perfectly. The idea that light exists as a particle with an energy related to its frequency. If a single photon, if a single bit of EMR is not causing the electron to be ejected, then it doesn't matter how much of it we have, we're still not going to get an electron ejected. Because more of it, more of that light, doesn't change the frequency and therefore doesn't change the energy. More light is not what we need to cause an electron to be ejected, but rather different light is what we need to cause an electron to be ejected. So if visible light is not causing the photoelectric effect to occur, we need what? We need ultraviolet, or we need X-rays, or we need gamma rays, something with a higher frequency, therefore something giving me a higher energy. If we are above that minimum frequency that we call the threshold frequency, and we have one single photon that is above that minimum threshold frequency, then we will get one single electron that's ejected. If we have 30 photons above that threshold frequency, what's going to happen? One photon below the threshold frequency, nothing happens. 30 photons below the threshold frequency, nothing happens. One photon above, one electron ejected. 30 photons above, 30 electrons are going to be ejected. Or 1,000 photons above the threshold frequency, then 1,000 electrons will be ejected. Let's say the threshold frequency is in that ultraviolet range. So visible light won't cause it, ultraviolet will. You got one photon of ultraviolet, we get one electron ejected. What if we get one photon of X-ray or one photon of gamma ray? What's that going to cause? One electron. Good. Still one electron. It's a 1-to-1 ratio. One photon, one electron, as long as you're above the threshold frequency. But what's going to be different about that electron, Patrick? Good. Yep, it's faster moving, it's more energetic. Because the original photon had a lot more energy. It gives a lot more energy to the photon. Therefore, the energy of the photon is going to be more. Therefore, the speed of the photon is going to be more. We learned 4 equations, well, 3 equations yesterday. One equation we already knew. The equation we already knew that's valid anytime you have photons, including the photoelectric effect, is HF is equal to hc over lambda. That's not the energy of an electron. It's not kinetic energy. It's the energy of a single photon. We also learned yesterday W, the work function, and the minimum energy necessary to eject an electron is equal to h times the minimum frequency necessary to eject an electron. But that's also equal to hc over lambda as well. What lambda do we have there? H times the minimum frequency, hc over the maximum wavelength. Max wavelength because frequency and wavelength are inversely related to each other. Next, we talked about the kinetic energy of the electron that has already been ejected. The kinetic energy of the electron, or the maximum possible kinetic energy of that electron, is equal to 1/2 mv squared. That's nothing new. We learned that in Physics 20. But that's also equal to QV stop. That kinetic energy can be converted to potential energy as you apply a potential difference to slow down and even stop the electron that's already been ejected. So the kinetic energy that it has as soon as it's ejected is equal to the potential energy that it has after it's been stopped. And it's that stopping potential that stops it. Finally, the last equation that we have is the one that we use most often, but the one that doesn't appear on our data sheet. It comes from the law of conservation of energy. What is it? We've got two things in a photoelectric effect experiment. We've got a photon that strikes the metal, and then we've got an electron that's ejected. What is it that starts off the process? What is it that has the energy to begin with? The photon or the electron? The photon. So we're going to say the initial energy here, EI, is equal to the energy of the photon. The final energy, EF, is going to be the energy of the electron, right? And we know that that is kinetic energy, EK. But EI is not equal to EF. EI is equal to EF plus whatever we used up in the process of ejecting the electron, which corresponds to the work function. So the law of conservation of energy says HF is equal to EK max of the electron plus W, the work function. Now, we can also replace HF with HC over lambda. We can also replace EK max with 1 FMV squared, or QV stop. And we can replace the work function with HF0 or HC over lambda max. Do whatever you got to do to make it work. There's 4 basic equations. The last equation we use most often doesn't appear on our data sheet, and we often have to sub in expressions for that last equation. But what you see up on the board is it. There's nothing else you're going to have to do with these photoelectric effect problems, other than maybe combinations of these. All right, we had 3 questions for homework last night on page 719. I'm pretty sure it's question 2 and 3 that we're going to have to go over here. Is that right? I don't know if you guys caught this or not. Question 2, you need the work function for cesium. The work function is given to you in one of the other questions that we did, a previous question. The work function is 2.1 electron volts. If you don't have that, or if you didn't spot that in the previous question, then this becomes not just a challenging question, it becomes an impossible question. That number would be given to you on a test. Now, it may be buried in a half a page of information, but it would be given to you somewhere on a test. Now let's solve question number 2. We're looking for the kinetic energy. We've got the wavelength, although it's in nanometers and we want to convert that to meters. We've got the work function in electron volts. Which equation are we going to use? I'm going to count to 5 in my head. Okay? Okay, nobody's answered the question yet. Which equation do we use? If nobody answers the questions within a few seconds, we're always going to try this one. If you come up with another one to try right away, then go ahead and try it. Even if you're wrong, even if the other one's not going to work, it's okay, because they're all valid equations. I'm just saying that if you don't know which one to use, try the last one, because it's the one that's most common. So let's say HF is equal to EK max plus W, the work function. But we don't know what F is. We do know what lambda is. HF is equal to HC over lambda. EK is what we're looking for here, plus W, the work function. Which Planck's constant do you want to use here? 4.14 times 10 to the minus 15 electron volt seconds, or 6.63 times 10 to the negative 34 joules seconds? 4.14, okay. So Patrick wants to use 4.14 electron volt seconds because we've got electron volts right here already, right? Can you do that? Sure you can. There are 2 situations in which you can't use electron volts. We'd have to convert this work function to electron volts and use this, to joules, and use the 6.63 value. But we haven't seen one of them here. When we introduce this equation, or this equation, we must use joules. We're using EK here, but we haven't introduced the equation that describes EK. So if we want to use joules, we can, but we don't have to. It's probably more convenient here just to stick with the electron volts. 4.14 times 10 to the minus 15 times 3 times 10 to the 8. We divide that by the wavelength, which is 400 times 10 to the minus 9. The work function is 2.1 electron volts. We take that 2.1 over by subtracting, and we end up getting an EK. I think it's 1.005, which is 1.01 electron volts. Good? There's no issue with using electron volts there, but there is an issue with using electron volts in question number 3. We're asked to solve for the maximum speed of the electron here for question 3. We're going to use the equation 1/2 mv squared. Let's solve for v. It becomes 2 EK over m, and then we square root that. But the kinetic energy can't be in electron volts here. Why not? Because we said that when you're using 1/2 mv squared or QV stop, you've got to use joules. You must use joules. So let's convert that to joules. Let's say 1 electron volt over 1.6 times 10 to the minus 19 joules equals 1.005 electron volts over x joules. X ends up being equal to 1.60 something. What do you have a value for that? Okay. 1.608 times 10 to the minus 19 joules. Now we can plug that value in joules over here. Multiply it by 2, divide it by the mass of the electron, square root it, and we should end up with a value that's 5.95 times 10 to the 5. Good? Good at that? All right, what I'd like you to do right now, please, is just take a look up at the board, diagram that you see up at the board here. It's a rough sketch of a simplified version of a burglar alarm. The first picture you see is when the burglar alarm is not activated. The second picture you see, you've got this burglar, Edward Scissorhands burglar, that's interrupting the beam of UV light and causing the burglar alarm to go off. I want you to take 3 or 4 minutes at your desks right now. Just think about what's happening here. See if you can identify some of the principles that apply here. See if you can identify how this burglar alarm is functioning when it's not going off and how it's functioning when it is going off. And see if you can give me some answers to those issues in 3 or 4 minutes after I've given you that chance to think about it. All right? Let's take those 3 or 4 minutes, see what you can do, and then we'll come back in a couple minutes here. All right, we've had a chance to look at this now. Tell me, somebody, please, what's happening in the first picture there when the burglar alarm is not being activated. Anybody explain one or more of the principles that are taking place here, Nick? Yeah. Okay, so that breaks the circuit. Okay, but why is that happening though? Why when the UV light strikes the sodium cathode, why is that making this spring extend, and why is it pulling this iron switch back? Okay, you're on the right track, but you're missing a little bit of principle there. Yeah. Okay. Okay. Be careful with the diagram there. This whole thing is the photoelectric cell. This sodium cathode, when light strikes it, the electrons are ejected from the sodium cathode. Okay? So what's happening here is this UV light must be above the threshold frequency, because when it strikes the sodium cathode, electrons are being ejected. Those electrons go around here. They go around this electromagnet with the soft iron core, which causes this iron core to become magnetized. As it becomes a magnet, it pulls this iron switch away from this contact right here, which breaks this circuit down here. There's a battery in this, but the battery's not doing anything because there's no complete circuit. The alarm's off. As long as something above the threshold frequency is shining upon this sodium cathode, then we're going to find that this alarm is not going to go off. What happens when this guy breaks the beam of UV light here? So why isn't the iron magnetized anymore? Why does this piece of iron here, this electromagnet, become not an electromagnet? Good. these electrons aren't being ejected from the sodium cathode because you have nothing above the threshold frequency causing the electrons to be ejected. If those electrons aren't ejected, you don't have a current going down through this wire, you don't have a current in this solenoid, you don't have an electromagnet. This spring that we see down here pulls this iron switch back and makes contact here. Now we've got a complete circuit over here with the battery, and the alarm goes off. What would be, I mean, this is a simplified burglar alarm. I'm not suggesting that every burglar alarm would be this easy to get past. But what would be a simple way for the burglar to get past this particular burglar alarm? Besides jumping over the light, that is, yeah. Yeah, if he shines a UV light at the sodium cathode, then he's going to bypass it, right? He can break that circuit any way he wants, as long as he shines a UV light on that sodium cathode. Now, why do you think that they would have used UV light here as opposed to any other kind of light? That's one reason, perhaps. You can't see it. Although, having said that, you always see in movies, right? You see these laser beams, you know, in the that the guys are trying to get across, whatever. You can't see them. You can't see a laser beam unless there's dust in the air or smoke or something like that. So you wouldn't see visible light either unless you put some smoke in the room or some dust or something to have something to reflect off of. So that could be partly it. So you can't see it, but only partly it. What's the other thing? We're overlooking something here that's pretty obvious. If the threshold frequency was below ultraviolet, then the threshold frequency would be somewhere in the range of visible light or even lower. If the threshold frequency was infrared or visible light, what would the guy have to do in order to bypass this? Turn the lights on. And all he has to do is turn the lights on. The visible light that comes from the lights would be above the threshold frequency and would cause these electrons to be ejected from the sodium cathode. So you got to have a threshold frequency somewhere in that range of UV light so that turning on the light switch isn't going to bypass this alarm system. Yeah, it's a great system, hey, if that's the case, right? All right, take a look at the picture that you see up here now, please. Yesterday we talked about this concept of the stopping potential, and I told you that the stopping potential was the potential difference required to stop an electron after it was ejected. And we said that we might want to do that so that we could find the threshold frequency of a particular material. Find the threshold frequency or other properties of a particular material. Maybe you're designing a burglar alarm and you want to see what metal to use so that you have a threshold frequency that's high enough that visible light's not going to bypass it. Maybe you're designing a calculator and you want to have a threshold frequency that's low enough that allows the calculator to be used when you're sitting in school without shining X-rays or ultraviolet on it. Bottom line is you want to find the threshold frequency or some other properties of this particular metal surface that electrons are emitted from. So how do we do that? Well, let's set up an experiment that we see up on the board here right now. We've got a power supply set up with a positive end and negative end. That causes a positive electrode over here and a negative electrode over here. We're going to shine photons that we know are above the threshold frequency because electrons are ejected. So let's get a really, really high frequency, cause the electrons to be ejected. Those electrons are ejected from this metal surface over here on the right-hand side, metal surface number 2, we'll call it. They're attracted towards metal surface number 1, the collector, and they're going to go around here. As they go around here, we're going to get a reading on the ammeter. Ammeters measure electric current. So as those electrons are going through that circuit, you're going to get an electric current there, and the ammeter is going to read something. Okay, what it is, whatever. It depends upon how many electrons are going through there per second. Let's flip this around now, though. Let's change the power supply so now that we have a negative side right there and a positive side on the other side. That's going to change my plates. My collector is now negative, and this thing over here is now positive. If I have photons of sufficient energy, then these electrons that are ejected will also have sufficient energy that they may still go all the way over here and go around the circuit like this. we will still read an electric current with this ammeter. But if we apply a big enough potential difference across this power supply, there's going to be a big enough potential difference across here that we may actually be able to stop the electrons that have been ejected. So this electron that's going this way slows down and stops. And a car going up the hill slows down and stops before it changes direction and goes back down the hill. We can't see these electrons. We can't physically see when these electrons have physically stopped. But when these electrons have stopped and aren't going through the collector, this current is no longer going to be flowing this way. What are we going to read on this ammeter? Nothing. There is no current on the ammeter. So we know when we've stopped the electrons by when the ammeter reads 0. What value is that? Well, we've just measured a stopping voltage or a stopping potential. From the stopping potential, we can get the max kinetic energy simply by multiplying the stopping potential by Q. Do it several times. Change the frequency. Okay, change the frequency of the EMR. See what the stopping voltage is and therefore the max kinetic energy is for each different frequency. Then plot a graph. Your graph would look something like this. Frequency on the x-axis, because that's what you're manipulating, the frequency of the incident EMR. Kinetic energy on the y-axis, because that's what's responding to that. We're going to get the kinetic energy by multiplying the charge by the stopping voltage. We're going to get a graph that looks like this. Straight line, but it goes through the x-axis there, somewhere to the right of the origin. There are three things that we're going to be able to discover from this graph now. The first one, the easiest one, is probably the most useful one. That's the threshold frequency. The threshold frequency is the frequency that's required for electrons to be ejected. In other words, it's the frequency that's required to give the electrons kinetic energy. Can anybody tell me from this graph, based on what I just told you, how we're going to find the threshold frequency? The frequency required to get electrons moving. Good. It's the x-intercept. Okay, at that frequency, electrons start getting kinetic energy. At that frequency, electrons start moving. So that's the frequency that we call the threshold frequency, the minimum frequency necessary to eject the electron. That's the easiest one. There's two other variables that we can find from this graph as well, though. And to find out how to get those variables, we need to go through that graphical analysis that we've learned through several of the activities that we've done. The equation from this graph, as with any straight line graph, is y equals mx plus b. The y-axis on this graph is ek. M is the slope. Let's replace the word or the letter m with the word slope. The x-axis is the frequency, and then the y-intercept. Can we get rid of the y-intercept here, by the way? Some of the activities that we've done so far, we've been able to scratch it off. Some we haven't. Can we scratch it off here? Is there a y-intercept here? Yes, there is. You see in this picture right now, it appears as if there's just an x-intercept. But think about this logically. If there's an x-intercept, it doesn't go through the origin. If it doesn't go through the origin, then there's also going to be a y-intercept. Now that y-intercept would be down here somewhere. It would be negative something, but it's still a y-intercept, right? That means that we can't get rid of the letter b here. Just like we couldn't in the last activity that we did, with the lens equation. Yes, it would. And I'll explain what that means in just a second here. Okay, you'll see. We have to find an equation on our data sheet or somewhere out of our head that goes along with this. It has the same variables, ek and f. It's going to be this one. hf is equal to ek max plus the work function. This one doesn't appear on our data sheet. It's the law of conservation of energy, but we know that we have to be able to remember that or derive it. Okay, we've used that a few times already. Let's rearrange this to take the same form. We end up getting ek is equal to hf minus the work function. Let's cross off things that appear in both. EK appears in both. F appears in both. What are we left with? Well, we're left with slope attached to F and H attached to F. Therefore, we're going to say slope is equal to H. Slope is Planck's constant. How do you think we found the value of Planck's constant? How do you think we know it's 6.63 times 10 to the minus 34? Because it's the slope of an EK versus F graph. What's left? B and negative W. The y-intercept here is the negative of the work function. In other words, you want to find the work function? Take the y-intercept, but take its negative value. So, Patrick, you asked just a second ago, wouldn't that be a negative EK? Yes. And that negative EK per se doesn't have significance because you can't have a negative EK. But the negative of that negative EK becomes the work function. Does that make sense? So it's kind of like, it's not really what's happening, but think of it like this, Patrick, okay? Think of it as the electron is waiting to get up to ground level. It's underground. It's got a negative potential energy. It needs to absorb a positive energy to get to the ground level and then go up into the sky. Okay, that makes sense? So a negative potential energy in a sense that it needs to absorb a certain energy, a work function, to get to the ground, and then it's free. The biggest thing here really is the graphical analysis, right? Okay, it's exactly the same thing as we've done for a number of the activities that we've done here now. Y equals mx plus b, get an equation for your graph, get an equation from your data sheet or somewhere else that matches up with that, and then let's figure out what the slope represents. Let's figure out what the y-intercept represents. Does that make sense? I hadn't planned on showing you the next graph, to be honest. But the last class, they were asking me a lot of questions about this whole graphing thing. So we went through a couple of examples, not even involving the photoelectric effect. But then we went through one more involving the photoelectric effect. You could see a million more. In fact, there's a good chance on your diploma exam you will see a graph that we've never seen before. I'd say it's about a 50-50 chance. That's okay. I'm not worried about that. Because as long as we know how to go through this analysis, we can deal with any graph that we ever see. Let me show you one more, though, that I normally don't show students. But I will this time just because last class were asking me a bunch of questions. This one's going to be the stopping potential as a function of frequency. That graph will take the same shape as the previous graph did. But clearly, finding things are going to be a little bit different because our y-axis is different. There are the same three things that we can find from this graph as from the last graph, but the way we're going to find them is going to be slightly different. Anybody make a suggestion how we might find the threshold frequency on this one, the minimum frequency at which electrons are ejected? It's also going to be the x-intercept. Let's think about that and why that's the case. Same thing as the previous graph. What frequency are electrons ejected at? Well, what frequency do electrons need to be stopped by a stopping potential? At what point do you need a stopping potential to stop electrons? When they're ejected. So when the stopping potential becomes non-zero, when you need a certain value of stopping potential to stop the electrons, that's the point at which they begin to be ejected. So that will be the minimum frequency. That will be the threshold frequency. That's exactly the same now as the other graph. Now the other variables are a little bit different. For this one, we're going to say, once again, y equals mx plus b. On the y-axis this time we have v stop. On the x-axis, sorry, m represents the slope. On the x-axis, we have f. Can we get rid of the b? We can't, because there is a y-intercept. Even though it's below the x-axis, there is still a y-intercept here. My equation from our data sheet, well, We don't really have one that has V stop and F in it, but we do have HF is equal to EK plus the work function, and EK is QV stop. So that works. Now we've got F and V stop in the same equation. Let's rearrange this one now on the right-hand side to take the same form. Let's rearrange it to solve for V stop. We get QV stop equals HF minus W. We get V stop is equal to HF over Q minus W over Q. Make sense? Let's cross off things that appear in both. V stop appears in both. F appears in both. What are we left with? Well, in this case, we're left with the slope is equal to what? H over Q. You don't see that graph all that often, right? The slope of this particular graph is H over Q, but if you do, it's easy to analyze here. What's left over here? B now. What's B equal to? B on the last graph we did was equal to the negative of the work function. Now it's equal to negative work function over Q. So if you want to find the work function here, you've got to take the Y-intercept and multiply it by the charge. Okay with those? Can we deal with that? Yeah. It's not that bad, is it? Once you get the hang of it. Remember we did this the first time, and it's like, what? What are you talking about? Now we've done it probably half a dozen times or more now with a bunch of different activities and a couple times in class. And now I think, at least I hope, that it should be becoming a little bit more clear for us. Let's take a look at a couple multiple choice questions here just as practice, okay? Take a minute here to take a look at number 115 at your desks. Okay, let's take a look here. How many people get A? B? C? D? Okay, let's take a look at the question here. And we've got a frequency here of EMR, not a threshold frequency. It's just saying that here's the frequency of the light. We've got a stopping voltage here, or a stopping potential. And we're working for the maximum kinetic energy here. We've got 4 equations. The simplest equation to use here is simply EK is equal to Q times V stop. Don't overlook the obvious, okay? You know what the charge is. You know what the stopping voltage is. You multiply 1.6 times 10 to the minus 19 times the stopping potential of 1.25 volts, and we end up getting C. All right, let's try the next one here. All right, let's take a look at this one again here now. 119, who said A? B? C? D? Okay, a lot of people didn't vote here. Are people still working on this? Okay, I'll give you another minute to finish this up here since there's still a few people working. All right, let's take a look at it here now. It says the threshold frequency for the emission of photoelectrons from the metal is 4.4 times 10 to the 14 hertz. That's going to be F0. Just hold on one second here, guys. That's F0. Here's F. Let's keep those two straight, okay? We're given 2 frequencies in the same problem. F0 is the frequency that you need to emit the electrons. F is not the frequency you need to emit them, but the frequency you have. It may be above or below the threshold frequency. In this case, it's above here. We want to find the max kinetic energy here. You know which equation to use? 5 seconds. If you don't, then try HF is equal to EK max plus the work function. Now, we don't know what the work function is, but we know that we can replace it with H times the threshold frequency. So we've got this value, we've got this, and we've got this. We can solve for the max kinetic energy here. Now, what value of Planck's constant do you want to use here, both here and here? 6.63 times 10 to the minus 34, or 4.14 joule seconds, or electron volt seconds? 6.63, because your answers are all in joules. Could you use electron volts for this if you wanted to? Or if the answers were all in electron volts? You could, because we're not using QV and we're not using 1/2 mv squared. That's the only time you've got to use 1/2 mv squared. Does that make sense? The answer is, for that one, D, is it? Okay, I'll trust you on that. I would like you to do, over the weekend, guys, please, 120, 121, and 122. Multiple choice questions, 120 to 122. That's your only homework over the weekend, other than studying for your test. Remember, Tuesday at lunchtime, Tuesday at lunchtime is your practice test for those of you who want to come by, okay?